Chapter 11 looks at more dealing with functions, and it also gets into logarithms, and it gets to exponential functions as well. And that's where you have something raised to a power of x, and we will get into a bit of those today, in fact, in 10.3, or 11.3, I should say. So in 11.1, we are looking at addition, subtraction, multiplication, and division of two functions. And two functions might be something like f of x, the function of x is what that means, is equal to 2x squared minus 1. And the other function is g of x. The function of x on g is what that one means. And that one might be x squared plus 2x minus 5. And as we look at these two functions, this is of course a parabola. This one's also a parabola. And what these two parabolas may be doing is crossing each other. And so they might have some different stuff that's taking place with them and so forth. So if they said, what is f of x when x is equal to 3? So what does that mean? Well, that means up here, I would replace x with a 3 and solve it. So 3 squared is 9. 9 times 2? 18. 18 minus 1 is 17. Okay. And over here, the same thing might happen. If g of x and an x is replaced with 3, what will I get? So I put 3 squared plus 2 times 3 minus 5. And so what ends up coming out of that one? So 3 squared is 9. 2 times 3 is 6. So 6 plus 9 is 15. 15 minus 5 is 15 minus 5? 10. Yep. And so that's what would equal if I just substituted these pieces in to each of these. And Hawks does have you do that, and it does have you put stuff into place, and so you can solve those, and I think we're all pretty good at doing that type of thing. Yes? Okay. Then it goes one step farther, because as you look at addition, subtraction, multiplication, and division, what all of those may look like is the function of f plus the function of g with an x after it. So what this means, and I'm going to put them all up here so we have every one that goes through addition, subtraction, multiplication, division. What this means is I take whatever the function is at f and I add it to whatever the function is for g. And so basically I'm taking those two things and I'm adding them together. Oops. Oh, that would help. Tell me that. I got to move this guy down a little bit. That will help. Okay, thank you for saying that. So f plus g means whatever the function is of f is going to be added to whatever the function is of g. So what that means in the two examples that I have is I take what f of x is equal to and I add it to whatever g of x is equal to, and I simply end up with what that comes out to be. So 2x squared plus an x squared is 3x squared. 2x doesn't add to anything, so I want to put them in order, descending from a square down to no x's at all. A negative 1 and a negative 5 ends up being a negative 6. So basically all I did was to take those two functions and add them together. So far so good? Yes? Okay. Now if on this one it said f plus g when they're at 3. Now what does that mean? Well, that means that if I'm going to add these two things together, I want to get that thing off of that pause so I don't accidentally bump it. What this means is what happens to these functions when x is 3. Now there's two ways of doing this. One is back up here. Remember we solved them both for 3? So you could solve each one individually for 3, and then this part, go down here and take 17 plus 10, and end up with the answer of 27. We can go through and add the two pieces together first, then go through and take what we have for the answer at the end and put 3 in place of what we had in that one and see if we still get 27. So 3 times 3 is 9. 9 times 3 is 27. 2 times 3 is 6, minus 6. Notice it still came out to be 27 when I did that. Okay. So that's what can happen with addition, and that's basically all the different pieces that we can possibly come up with for an addition problem. So we'll put addition up here. In subtraction, same kind of thing, but in this case it's f minus g of x. So what in the world does that mean? Well, of course it means the exact same thing. The function of x minus the function of g of x is what I have. So it's 2x squared minus 1 minus x squared plus 2x minus 5. But when I do my subtraction, what has to happen with that? On which piece? The second. I got to change all these signs. So 2x squared minus 1 minus x squared minus 2x plus 5. Now don't forget to change all signs because they all have to become something different. And so now I have 2x squared minus an x squared is an x squared. Negative 1 and a positive, well, this 2x needs to come in there, minus 2x. Negative 1 and a positive 5 is a plus 4. And so that becomes my piece that I have if I take these two and subtract them. So then, again, if you have this piece, oops, and a 3 in here, that means what takes place when there's a 3 involved. So once again, because I solved them, was 17. Minus 10 was the g of x, so my answer comes out to be 7. And if I plug 3 into here, 3 squared minus 2 times 3 plus 4, 3 times 3 is 9, negative 2 times 3 is negative 6. And sure enough, 9 minus 6 is 3. 3 plus 4 does end up equaling 7. So you can do it in two different manners, whether you want to go through and solve it first, then plug in your number, or whether you want to do it the opposite way. Now sometimes they reverse your order in here, so it might be g minus f of x. And that's going to change my whole relationship that I had. My answer is not going to be the same as what I had up here, because when I change it, now the x squared plus 2x minus 5 comes first, minus the f of x portion, which is 2x squared minus 1, and so that whole thing changes in there. I think you noticed that, don't you? Because this stays the same. This sign's change, so I have a negative 2x squared and a positive 1. So then my final answer is x squared, and a negative 2x is a negative x squared. 2x comes along. A negative 5 and a positive 1 is a negative 4. And notice this is different than the above one. What makes it different is basically all my signs have changed in there to make my difference. That's not always the case, because sometimes different things can affect that when you do it. These aren't hard, right? As long as you keep track of who comes first, okay? And make sure you put them in that correct sequence, in the correct order. The second one, or third one, I should say, is multiplication. So in multiplication, it's f times g of x. So if I multiply those things together, what's going to happen? My two pieces, I guess I need to write those back up here again. F of x is 2x squared minus 1, and g of x was x squared plus 2x minus 5. So then if I multiply that, I need to take f of x times g of x. So that means I'm going to have 2x squared minus 1 times x squared plus 2x minus 5. And so our rules that we learned way back when come to play in here because I need to multiply. So 2x squared times x squared gives me 2x to the 4th. 2x squared times 2x is a plus 4x cubed. 2x squared times a negative 5 is a negative 10x squared. Multiply the negative 1 through, gives me a negative x squared, a minus 2x, and a positive 5 at the tail end. So when I multiply them, my answer is 2x to the 4th plus 4x cubed minus 10x squared, no, minus 11x squared. We've got to combine those two. Minus 2x plus 5. And that becomes my answer if I multiply those two together for what comes out of it. So really, it's just an application and taking what we learned with polynomials, with adding and subtracting and multiplying and dividing, and sticking it all together and making them into functions and doing stuff that are function related with what we happen to have in there. Okay? And the final one is division. Oh, also we could do the f times g at 3, but when I do that one, it's simply going to be, I think we had 17 and 10 before. So 17 times 10 is 200, not 210, what am I thinking there? 170 is what I would end up with for that one. And if you plugged your 3 into all of these spaces, work this whole thing out, it will also come out to be 170 when you're done with it. So this whole piece would equal 170 when you work with it. And division is probably really the easiest one of all of them, because normally, and this can also be written as f over g of x, meaning that I'm going to divide those two. So basically, it just means simply put 2x squared minus 1 all over x squared plus 2x minus 5. Now, in some cases, when you work with these, this top part might factor, and your bottom will factor, and you have some stuff that you can cancel out. In this example, there isn't anything that cancels in there, so there is no cancellation of stuff. If you look at this bottom piece, it also has a restriction on its domain. Remember, it can never equal 0 for my denominator. In this case, I can't factor it, so I'd have to go use my quadratic to figure out what that would be. All right? Now, when you are working in your Hawk section, they don't give you anything that difficult. This one's just that example that they start out with, and so that domain might be something on a different order. So if you happen to have had something like x squared minus 9 all over x minus 3 as your value that you happen to have, in other words, f of x is equal to x squared minus 9, and g of x is equal to x minus 3, and I want f divided by g of x, that's what it would come out to be. And when I say about reducing, x squared minus 9 becomes x plus 3 and x minus 3, and so I have an x minus 3 in my denominator, but what happens? These guys cancel, so my final answer is just x plus 3. But the domain restrictions still apply, so what can x never ever be? So x minus 3 equals 0. So if I add 3, x can never equal 3. And we found that out in the last, actually 10.6 is where we did some of these, where we looked at denominators and they couldn't be 0. And so we worked with that part. So keep that in mind that x can never equal 3 when you're doing some of these. Domains are not limited in multiplication because your multiplication comes out to be just straight values. They're not limited in addition, and they're not limited in subtraction. If, though, you have this, for instance, if f of x is equal to 2x and g of x is equal to the square root of x plus 1, there's some limits on this one, though, because what happens with the square root? I can never have it be equal to a negative number under there, right? Because I can't take the square root of a negative number. So how we took care of that is we set it also equal to 0. And we found out that if x is a negative 1, or is greater than, I guess I need to put that in there, greater than or equal to. So if x is greater than or equal to a negative 1, I'm fine. But if I get less than that, I'm in trouble, okay? Because this will not work. And so then they may give you f plus g of x. And so when they give you that one, that's just basically 2x plus the square root of x plus 1. If they give you g minus f of x, what happens with that one? Well, that just means I need to take the square root of x plus 1 and subtract from it 2x. So my order just changes in there. If it were a multiplication, g times f of x, because multiplication is commutative, it doesn't make my order any different. So I have the square root of x plus 1 times 2x, or just simply 2x, the square root of x plus 1 for my answer to that one. Be real careful when you type this stuff into Hawks. If you miss a square root or if you miss a plus sign, that was my killers. I accidentally forgot to put a plus sign between something, and it said, sorry, you're wrong. Okay, so keep that in mind, that is what ends up happening with those. And then if you do division, if I have g divided by f of x, that just simply means I have the square root of x plus 1 all over 2x. And so I get all my answers that way with those. So do you think you're okay or not with this piece? Again, it's just paying close attention to what you happen to have within your functions and within the pieces that you pull up and what you come up with for those. So it's just a matter of being careful. Follow this. So whatever it says, if G comes first, F will come second. So you want to make sure you get that order down, and so you get those going in the right direction. One other thing that happens in this section is they give you a graph. And on that graph, it may have dots, and the dots are in different colors. So up here we have purple dots and we have red dots. Each of these represents a function. So what we find with these functions is we start looking at them is that there's stuff about domains that I happen to know. So if I work with this first one and I want to come up with what its domain happens to be. Domains, remember, are every x that we happen to have. So the domain of the function of f, the domain is every x that I happen to have. So my domain is made up of a -3, a -1, a +1, a +2, and a +4. We all okay with that? Because all I did was pick up my x values within my points, and so that became my domain. What's my domain of g of x? And if I look at its domain, notice if I look at my graph, the purple points are all right in line with the red points. Do I see that okay?
We don't have color.
You don't have color? Oh, that's not nice. You're supposed to have color. I don't know what happened.
A little color, but
They look a little colored, but not much. Well, anyway, these are the domains of G, and notice they're running right in line with all the other values that are up there. And so if I look at my domain here, -3, -1, 1, 2, and 4. So in this case, my domains are exactly the same. But if I looked at ranges in relationship to this, what would happen to my ranges? Ranges, remember, are which letter? Y's. So 4, 7, 4. Do I need to write 4 again? Probably not, because it's still a 4. 1 and a -3. And if I look at my range on the G of x, what's it going to be? Well, the range on G of x is 1, 9, -1, -4, and 2. So my ranges are different, but my domains are the same within these. So then if I said, let's add them together, well, what's going to happen then? Well, I can't add and combine stuff together as far as domains happen to be, because the domains are going to be, they won't change within your domain part. But what makes a difference is what happens when you take these 2 points and find their locations. So if my question said f plus g of x, if that's what I was asked to do, and I have points, I just simply look at these 2 points. I know the first value of my domain is going to be a -3, because that's the exact same as what I have. But a +1 plus a +4, what does that give me? +1 plus +4? +5. And if I take the next point, and if I look over here, 7 and 9 added together, when I'm at a -1, what's 7 plus 9? Whoops, 16. I don't think I'm keeping all my pieces on here. And then if I go to the third one, a +4 and a -1 at 1. What's that going to give me? +4 and a -1. +4 plus -1, I think last time I did that was a 3. And then if I take a look at the other one, it's out 3 points. And a +2 and a -3 leaves me with a -1. And finally the last one is out at 4. And I'm up 2, and I'm, or did I just do that one? No. I think I'm off one here. 3, -1, and -4. Oh, that should be a +1, and a -4 should be a -3. I did the last one. +2 and a -3 is a -1. So I had one off. This one wasn't right.
I'm confused.
You're confused? Okay. Basically what I'm doing is I'm looking at the location of this point and the location of this point. All right? They both have the exact same domain. All right? So then what I'm doing is this point is located at -3, 4. Okay? This point is at -3, 1. All right? But because I'm adding, because my problem said f plus g, I'm going to these points and I'm adding the y portion of my point. So 4 plus 1 is 5. And I come up with a brand spanking new point, and the new point is at -3, 5. And that's the addition of those. It'll make more sense when you get to see a regular graph that has some of these combinations in it, because then you can start to see what ends up taking place with it and what makes a change in it and an adjustment. It's hard with just points, but in Hawks they gave you just points, and they ask you to combine them together. So if I go to this next next pair of points. This one, the top one, is up at negative 1, 9. The one below it is at negative 1, 7. So my rule says take only the y values and add them together. So 9 plus 7 is 16. So I come up with a brand spanking new point. My new point is negative 1, 16. And that's the combination of those two. And then if I go to this pair, this one happens to be at 1, comma 4. This one happens to be at 1, comma negative 1, and 4 plus 1 plus a negative 1. What's 4 plus a negative 1? Gives me a new point of 4 plus a negative 1, a new point of 1, comma 3. And so that becomes the new value that sits between these two. And so then what you'd find is you'd start plotting these points. So 1, 3 would be here. I can't plot 9 or negative 1, 16. I can plot negative 3, 5. So what you start having is the red dots are going, if I just join those all together, the red dots are doing that. The purple dots are going and doing one of these numbers. And the ones in between are going to be giving you another graph of the combined added pieces in there. So it's just getting a combination of stuff that they will do. Also in Hawks, they'll give you a function. So let's try it this way. Let's see if we can do it a little bit different. So on your graphing calculators, so grab your graphing calculators, we are going to put in f of x, or the function of x, is equal to x plus 4. So stick that on your graphing calculator. Then we're going to do another one, g of x, on y on the next axis down. But this time we're going to put a negative 1/2 x minus 2. So do you have both of those on your graphing calculator? Hopefully. And what shape does it end up becoming? Well, let's put a graph up here of what this looks like. So if I graph the first one, I'm up 4. Slope says rise 1 and run 1. So your first graph that you have on your graphing calculator should look like so. Correct? Second graph, I'm down at negative 2. My slope says go down 1 and over 2. So it looks like so. Let me get lined up here. All right, ready for that? Okay. Now, if you go second, hit your graph button and go to your table. Now, your table lists all of the points that are in relationship to these two. Okay? Everybody find that? So, what is, if we have f of x, give me 3 points. And we're going to get some common stuff. So give me, what is the value when x is a negative 1?
3 and negative 1.5. Right? No. Is that what you guys said?
When I'm at a negative 1, oh, I'm not even. Find me some things that are even in there. I don't know if we can find stuff that's even.
0.
What was that?
0.
0 is? Okay. So what's 0's value?
4 and negative 2. So 2. Right?
0 is 2? When I'm at 0 on purple, I'm at 4, really.
Yeah, there's 2 numbers.
Oh, there will be 2 numbers, because you have also g of x. So when I'm at 0 here, I'm down at a negative 2. Yes. Okay. So you have the two graphs going on there, okay? What's another one that's solid? 2. So when I'm at 2 for my first graph, what's my point? What's my value? 6. And when I'm at 2 on my second one, what's my value? Okay. All right. And one more. You got one more in there? Negative 2. Okay. What's the other point of negative 2? 2. Okay, that's the first one. And what's the other one? Okay. All right. So what I just found is on these graphs, there's these points. We all agree? Okay. So if I wanted to take F and add it to G at X, what would my new values be? So my new values are going to be these points, but the Y piece is going to change because I'm going to add them together. So what's 4 plus a negative 2? 2. And what's 6 plus a negative 3? And what at a negative 2 is 2 and a negative 1? Yeah. Okay. So that's the graphs added together. Before we were just adding functions together, but when you add graphs together, what do we end up coming up with? Well, as we start looking at this, where are these? Well, when I'm at 0, it tells me my new graph, I'm up at 2. My new graph, when I'm at 2, I am at 3. I don't know, are those showing up? I hope so. When I'm at a negative 2, I am up at 1. So what I have created is if I take those two and add them together, I've created a brand new graph of what their combined values happen to be. And so that's kind of what it's asking you to do, is to say, what is that new graph going to look like? Okay? Now leave those on your calculator, those two that you have on there, those functions. And in Hawks, it does go through in your instructions and tells you how to do this part of getting what that new graph would look like on your calculator. So let me get my pieces in here. X plus 4 and a negative 1 divided by 2x minus 2. Go down to your third bar in there, and we're going to go through and combine these together so you just get a picture of what they happen to look like on your graph. So first we're going to enter our two pieces, which we did. Second, we're going to go to the vars key, the variables key, which is right here next to your clear button. I don't know, I'm going to get this up here a little bit farther. Your variables key is right here. So go to that key, leave it inside of there. Then you are going to move to Y varies on the next part over there, and you are going to let's see, select your it says select Y1. I guess I need to select functions here. Yep, select functions. Select Y1, hit enter. It put Y1 into my graph field. I don't know, is that showing up? Move it down a little bit here, maybe. Then go back and put a plus sign in there because we want to add them. And then go back and do varies, or variables. Go over to Y varies, hit enter for functions. Then go down and hit Y2, hit enter. And now what it's going to do when I hit graph is it's going to show on your graphing calculator that first graph coming in, second graph, and it's going to show the one that we had just found up here by combining our variables together as being the combination of those two. And so that ended up going right straight through in the center of those. And so you end up with what your piece happens to be for that. So that is what your combination happens to be. So if you want to write down those, go into your instruct, and it will show you where that's at. Now, do they use it a whole lot in the instruction part? No. They spend a whole lot more time on just getting the addition, subtraction, multiplication, and division of variables, or not variables, but of functions, than they do with graphing in this section. But it does show up in there, and so it just kind of gives you an idea of where that's at. But it is in your area within your instruct if you want your step-by-step with that. But we just added our points together, basically, is we added our y values within our points and came up with that. And it will ask you in your instruct to come up with these, and it will ask you to figure out what your parts are going to be. There are a couple of those that do pop up. So that's how you go about that. Does it make better sense now? Maybe than having just the points and the dots. But again, they will do that kind of combination. You'll have to look through there and find your dots that relate to each other. Okay, so that ends up taking care of, basically that was 11.1, and going through and doing some of these. Do we need to do any extras in there? Are you guys okay? Pretty good? Okay. So, moving on. 11.2. 11.2 looks at a function of a function. You're probably saying that sounds kind of strange, weird. What this means is basically it is going through and sticking a function inside of a function, or putting a function inside of a function. I know it sounds worse than what it is. I told my students a few years ago that it's kind of like the M&M and the pretzel. Remember the M&M and the pretzel commercials? Pretzels say, no, I don't want to get inside you. No, I don't want to do that, you know. So this is kind of the same thing. You're going to take the pretzel and stick it inside of the M&M. Because what is involved with this type of stuff, there's two ways in which you see these. One is the function of g of x, meaning that what I basically have done, if you notice, there is no addition, there is no subtraction, no multiplication, no division in here, is what I have said is I've taken g of x and stuck it inside of what f happens to be. These are exactly equal, and you see them written both ways. So you see them written as fog, or FOG, that you happen to see. And I think this one, you see it in certain textbooks. This one you see in certain textbooks. The other way of seeing this is where f of x is stuck inside of g of x, and that is g of GOF, or GOF as we refer to it sometimes in math. And these end up being the two kinds of combinations of what you will end up seeing with those. Now, what in the world does that mean? Well, if we have two functions, let's say f of x is equal to 2x plus 4. G of x is equal to x squared plus 1. So when you do this is when you replace or take g of x and stick it inside of f of x, is everywhere there is an x, replace it with the other function. So I'm going to replace it with the other function. So if I have f, replacing it with g of x, or f of g with x, that means I'm going to take what this thing is, or the M&M, In other words, I'm going to replace it with x squared plus 1 plus 4, and then I'm going to solve it for what it's asking me to do. Well, in this case, it's asking me to distribute 2 times x squared is 2x squared. 2 times 1 is 2 plus 4. But to stick the whole thing together, I'm left with 2x squared, positive 4 and a positive, or positive 2 and a positive 4 is a positive 6. So my answer, when I stick this piece together, is that. All right? Not bad. It's just, pay attention. It's kind of going backwards here, because you've got G is going into F. All right? So remember that. It's not F going into G. That's usually the one common mistake that's made, is you start from the right to the left, like we, or from left to right, like we always read everything, but in these, you want to reverse it. In this case, put G in F for X. So you want to stick that piece in there and replace it. If you had a G or a Goff of X, that one's going to be a little different, because with this one, now my M&M is G and my pretzel is 2x plus 4, so I take x, the x squared up here, replace it with 2x plus 4 squared plus 1. And so what do I get? Well, I got to square this thing, so that means I have 2x plus 4 times 2x plus 4. And so what comes out of that? 2x times 2x is 4x squared. 2x times 4 is a plus 8x. 4 times x is 4 times 2x is 8x, and 4 times 4 is 16. Don't forget my plus 1. So my final answer to this thing is 4x squared plus 16x plus 17. And that becomes my answer when I stick g of x in, or put f of x in for whatever x is in g of x. Yes or no? Let's take a look at a few more of these guys. So we're replacing, again, taking and sticking that value inside of those so that you get your combination or your values to come out. Okay, let me flip that and get another one up here. So if f of x is equal to the square root of x minus 3, and g of x is equal to x squared plus 4, what will I get if I have f of g with x outside of it? What will happen? They don't ever put numbers in this one, so you always just kind of have your combinations. So if I have this one, what has to take place? Well, g needs to go in where x is at. So I have the square root of x squared plus 4 minus 3, because I'm just replacing x with it. Can't do a whole lot with this. X squared plus 4 and a minus 3 is a minus 1. Doesn't help me because I don't end up with two factors that are the same to pull anything out, because I got a square root out there. So that's just basically my answer to that one. If it were reversed and we had a g of x, or Goff in here, G-O-F, what we would end up doing is replacing this x with that. So the square root of x minus 3 squared plus 4. So when I square a square root, what happens? Comes out. So x minus 3 plus 4 is x plus 1. And so, oh, this should have been a plus 1 over here, not a minus 1. And so we get x plus 1. So you get two different routes with those. So you're substituting and replacing, and you're starting with f and putting it into what g happens to be, and replacing your values in there. for those. Yes? Fully? Need to do another? Yes? Okay. Let me find another one in here. F of x is equal to 7x minus 4, and g of x is equal to 4x squared minus 3. And if we have an f with a g of x inside of it, so that means wherever I've got this piece has got to go in place of that. So I have 7 times 4x squared minus 3 minus 4. Don't forget your minus 4 because you're only replacing the one piece. So 7 times 4 is 28x squared. 7 times 3 minus 21. Then finally, minus 21 and minus 4, because those are the only two that combine, gives me a negative 25. All right? And that's my answer to that one. If it were the other way, then I would have to put this in place of the x squared. And that one involves a little bit. So if I take this and square it, 7x times 7x is 49x. Negative 4 times a negative 4 is a plus 16. And my rule says if I multiply these two, get 28 and double it, I get a minus 56 x in the center. I think that's right. And then 4 times all of that. 4 times the 49 is 196. 4 times 9 is 36. 4 times 4 is 16 plus 3 is 96 squared I need on there. 4 times 56 is going to give me 224. And finally, 4 times 16 is 64 minus 3. My final answer, minus 224x. 64 minus 3 is a plus 61. And the nice thing about these is you don't have to do anything else with that. You just leave it there.
Where did you get that? Why is it squared? Not 5.
Why is what squared?
Why is 7x minus 4 squared?
In here?
Yeah.
Because I'm replacing x.
Oh, yeah.
Okay?
Okay.
So remember, you're taking this piece, this x piece, this piece right there, and you're going to take this and you're going to put it in its place. Okay? So you're yanking out that x and sticking the other one in it, in its place. Okay. Yeah. Good question, though, because it looks like, wait a minute, how did it become squared? But that's because this x in here in my g of x is squared. So therefore it has to be squared in the other part. Yep. Better? We need to do another one. We good? Okay. All right. With that part. This section also has, it talks about looking at things and finding out if they are are a true final function-to-function connection. And what that means is are the graphs in one-to-one correspondence. And what that means is that every x has only one y, and every y has only one x. Okay? Now, it sounds kind of probably more complicated than maybe what it is here. But if you have a straight line is considered to be in one-to-one correspondence because everywhere I look at this, if I find this point right here, this point only has one point connected with it. There is no other value in here that has that x value or that y value, and so it's in one-to-one correspondence. So if you have a straight line, you might have the points of 1, 2, 2, 3, and 4, 5, and they're in, well, this should be a 3 here. They're in one-to-one correspondence because nobody's sharing anything. Every y has only one x, and every x has only one y. We okay with that part? This 1 is only associated with that 2. This 2 is only associated with that 1. There is no other values in here that have a 2 into it. If you have something like 2, 5, 4, 5, and 4, 3, that is not a one-to-one because notice this 5 is shared over here with a 4 and with a 2. This 4 is shared also with a 5 and a 3. So this is not one-to-one correspondence. This one is. Again, no sharing. If you do a vertical line test, quite a while back, we talked about vertical line tests and finding out whether something was a function. We did that. But we're also going to add in here a horizontal line test, and it has to meet both. So if every vertical line or vertical piece you have only hits on one x, but every horizontal hits on one spot on your graph, then you do have what's called the one-to-one correspondence in your graph. To take a look at a couple of these, I did put some on graph paper, so I didn't have to write them out, so you can kind of get an idea of what's one-to-one and what's not. If I look at my parabola, and if I do a vertical line test on my parabola, I would say my parabola is a function based on what I know about vertical line test. But it's not in one-to-one because as soon as I go through and I draw a horizontal line on here, what happens? My horizontal line, it hits in 2 spots in here, and those 2 spots makes it so it's not in one-to-one correspondence. So this is a no. And Hawks will put graphs in there and ask you whether they're in one-to-one correspondence. And more than likely, if you check a horizontal test on it, that's what's going to tell you whether it is or whether it isn't. Vertically, this one is a function, but horizontally, it's not in one-to-one correspondence. What about the line? Is that a one-to-one? Yeah, because every time I do a horizontal line test, what happens? Every horizontal line I can put on there is going to hit one spot. Every vertical line is going to hit only in one spot, so it's in one-to-one correspondence. This next graph is a graph of a cube. Is it in one-to-one correspondence? These kind of taper. They don't ever run exactly next to her. They're tapering out a little bit as they go. So it kind of looks like if you do the vertical line test, like it's not going to hit at one spot, but it does. And horizontally it does too. So we could say this one is yes. That every x is associated with only one y, and every y is only associated with one x in that one. And then my ellipse over here. One-to-one correspondence? No. So this one would definitely be a no because it does not compare and it doesn't look exactly the same with that. So that one's definitely a no. So I don't have any one-to-one with that one. Okay. So one-to-one correspondence, it's just basically looking to see what you have. Now the importance of that is when you look at exponential equations and you look at logarithms, logarithms are a reverse or an inverse of a value. So we need to take a look at what's meant by an inverse. And an inverse is the opposite. And to be an inverse, the function must be in one-to-one correspondence. meaning that I can't have any shared values in there, because what happens is an inverse doesn't take place, because you end up having combinations of stuff that happens with it. So in an inverse, the y becomes the x. So y becomes the x. So if I had a couple points, 3, 2, 4, 9, and 7, 8, if this were the function of x, and I want the inverse function, and what happens with an inverse function is they stick a little tiny -1 up there. Or this could also be written as f to the negative first. Either way, you might see those two. So what that means is within my points, if my y's become my x's, then what that means is in these points, the 2 becomes my domain, the 3 becomes my range, the 9 becomes my domain, and the 4 becomes my range, the 8 becomes my domain, and the 7 becomes my range. And so what happened to get the inverse function of this is the points reversed, and the points switched places, and came up with different values in there for those. And you come up with different combinations and different spots and different locations within it. So if we go back to our graphing calculator here for a minute, and go back to your y equals, we're going to clear out y2, we're going to clear out y3, and we are going to only look at that x plus 4. So you guys got just x plus 4 on your calculator, hopefully. So what does this graph look like? Well, its graph's just a plain old ordinary straight line. I guess I should get my window to be in the correct format here. Straight old normal straight line on my graph, right? So if I want its inverse, what would its inverse happen to look like? Well, if I go back to my graphing, to my graph paper here, and I just graph that thing. On here. And my graph was y equals x plus 4. So that means I'm up at 4. 1, 2, 3, 4. Slope says rise 1 and run 1. So here's my graph. This is what the function of x happened to be. What's its inverse going to look like? Well, if I go to my table, so second to my table, I see all kinds of numbers in here, and I see all kinds of point values, correct? So if I'm going to do an inverse of this thing, what in the world does that mean? Well, if I want the inverse of x plus 4, that means every x that I have is going to become a y, and every y is going to become an x. So if I look down my numbers here, I'm at a -5. I don't know where you guys are at. So let's get something that's a little bit more reasonable. Let's go with -2, 2. So where is a -2, 2? Well, a -2, 2 is right there. But I want to reverse it. So I really want to graph for my inverse. I want to graph a +2 down 2. +2 down 2. That is the inverse of this point. Okay? If I do another one, 0, 4, then I want to go 4, 0. 1, 2, 3, 4, 0. Okay? Because I'm reversing them, remember. 4 is going to become my, what's my y right now, is going to become my x. Okay? And so I get its inverse. So then if I do one more, 1, 5. 1, 5 is here, but I want to do 5, 1. So what have I found? Well, and I wish my colors showed up for you guys up there, is I found, my pen decides to die on me. I found its inverse. Its inverse is kind of the mirror image of what it happens to be. And so that's its opposite. That's its f at a negative 1 of x. And so it's its inverse of what happens to have taken place with it. That's great if we could show pictures of everything we did, but we can't show pictures of what does take place with that. Does that make sense to you? Because all I just basically did is made these become my x's and x's became my y's to get my inverse. Okay. So, and in Hawks it has you reverse some numbers, but it doesn't have you reverse your graphs necessarily within that. But it does end up showing you a couple other things that pop out in here too. Graphing wise, if you have a graph that does this, its inverse is going to do something like coming up here and going up this way. So its inverse is going to go in the opposite direction of what it happens to be. If you have lines that cross each other, then your lines may end up going and doing something on this order. One line might go this way, and its inverse will go the opposite way. And so you've got some combinations of stuff that end up taking place there. But they all have to be in that one-to-one correspondence. As we move away from concrete, these are concrete because you see pictures of them. If we take our f of x equals x plus 4, and we say, oh, what is f, or the inverse of it? What in the world is the inverse going to make it become? So if I look at the inverse, what I have to do with that, so the steps to find an inverse. So first off, you're going to set the function equal to y. And remember that f of x is the same as y, or g of x is the same as y if I'm going to graph those. So all I'm doing is just putting a value in front of there. Step 2, change all y's to x's and all x's to y's. And then step 3 is solve for y. And that will give you your inverse.
What do you mean solve what?
I'll show you in a minute. Okay. Step 1, because I've got my function, I'm going to set equal to y. Right? So that's step 1. Step 2, change all y's to x's and all x's to y's. Okay. And then what we're going to do is we are going to solve for y's. So that means I need to get y by itself. So how do I do that? I'm going to get y all alone. What do I got to do? Well, and minus 4. So I get x minus 4 is equal to y, and that is my inverse. So the inverse of f of x is x minus 4. And I can prove that it is if I bring in my graphing calculator and we go back to y equals, put in my inverse, x minus y, or x minus 4, hit my graph, and notice I get the graph I created. Because remember, we created one because we switched our x's around and our y's around, and we ended up with that piece that was in there. Okay. Back at looking at some inverses, because we left off with that inverse part. If they give you f of x equals 5x plus 2, and say find the inverse function. So find the inverse function. And the inverse function means that I'm going to set it first equal to y. Then I'm going to change x's and y's. So I'm going to put a y in, or an x in where the y is at, a y in where the x is at, because I'm reversing it and getting an inverse piece of it. So now what happens there? So now I got to solve for y. So that means I need minus 2 from each side. Finally, to get y alone, divide by 5. So I find y is equal to x minus 2 all over 5. And so the inverse function with that little superscript -1 in there of x is x minus 2 all over 5. And that's its inverse. That's its reverse of what we happen to have had with that one. If they give you the function of x is equal to 3 over x plus 3, and it says find the inverse, once again, set it equal to y. Yep. Set it equal to y. Okay. Replace y with x. Replace x with y. And solve for y. So since I got a denominator, that means I need to bring this thing up above. So that means I'm going to multiply every side by y plus 3. So that gives me x times y plus 3 is equal to 3, because these guys cancel. Move my x over, because I don't want to distribute, because that's going to give me x's in more than one place, so don't distribute there. So that's y plus 3 is equal to 3 over x. And then finally, minus 3. And we get y is equal to 3x minus 3. And that will be your solution that you put in there. Be extra careful when you put this stuff into Hawks. Make sure that you keep your pieces separated. Make sure you put the right number in. When I did mine, I was having problems in not putting the right number in that spot. And so you want to, and don't ask me why, I guess it was because I had other things I was thinking about or something. But be real careful and make sure you put that piece in. The other one function that they give you a lot of, it seems like Hawks likes to have you manipulate this, ones that look like this. And those happen to be g of x is equal to 3 over x minus 3. They tend to like these for some reason, and you will find bunches of them in your solving, so you want to watch and make sure that you are careful when you replace your y's. So set it equal to y. Replace x for y and y for x. Now to do this, I need to add 3 to both sides. So I have x plus 3 is equal to 3 over y times every side by y. So I get y times x plus 3 is equal to, these y's cancel, plus 3. Then divide by x plus 3. So we find y is equal to 3 over x plus 3. And again, they like lots of these. So you'll run across bunches of these with your inverses. At least I did. I don't know. Maybe yours might come out differently, but the ones I had a tendency to give me a bunch of things that look like that one. So be careful with it and make sure that when you replace it up here that you get your pieces moved in the correct format and the correct way with those. Then it also throws in there some of these things where it gives you a graph and says, is it a function or not? What would you say? No. Simple. All you gotta do is click no, and you're done. Okay? So if they give you a graph, you need to pay attention to what shape they're giving. Sometimes the graph they give you might be one of these, and would I say that's a function? Okay. That is a yes. Yeah, so we have a yes on that one. So we know that one does end up becoming a function when you're working with them. What do you think? More? No more? We're good? Okay. As long as we're good with that one, that's great. And again, that takes care of 11.2 and stuff with that part. 11.3 is looking at exponential growth. And in exponential growth, so far the things that we have had have been things that look like the function of x is equal to x squared plus 2x minus 1. We've had lots of those. We've had this variety where we had g of x equals x or 4x plus 2, straight lines. We've had h of x is equal to the square root of x plus 1. We've had those kinds. This kind, remember, gave me a graph that looked like so. This one gave me a straight line, and the one up above gives me a parabola shape of some sort because of that x squared. The shift and the change with these next ones is that they are still functions, but in the function, instead of having x on the bottom, they have x as an exponent. So the x is an exponent. And we need to take a look at what effect that has. And that's where you're going to use your graphing calculator a bit with these so that we get an idea of what the graph looks like. In Hawks, they will give you 4 graphs, and you will have to pick out the correct graph. And just by comparing it on your calculator is what you can do. So if we bring our graphing calculator back in here, clear out what I have in there. What do I find? Well, if I put this into my calculator under my y equals, I have 2 caret x. Now, whoops, no, I don't have that. I don't want that. 2 caret x. There, now it looks right. And so what in the world is this going to show me? So if I look at my graph, hit my graph button, it's going to show me this piece. And what that piece is doing is, as I look at what's taking place, it's approaching the x-axis, and then it's crossing up here, and then it's shooting up and going rapidly up, rapidly in a direction, in so forth with that. And so as you do that, you end up seeing a major growth that takes place within your exponents, because the larger x is, the larger the values happen to become as you start working your way up and getting your square in there. That kind of, I don't know if you guys ever heard about in ancient times, this guy asked the ruler, he says, I will work for you if you give me 1 grain of rice per day and double it. The emperor says, sure, that sounds real easy. So, but what happened is it was this exponential growth, and before long, the guy owned all of the rice in the area just for working for 1 grain of rice on the first day. Because what exponentially happened is it ended up getting larger. And so in science, we work with these when you start looking at bacterias that grow, because bacteria have a tendency to work on an exponential growth. You may start out with 1 over here, but as it doubles and as it triples and as it keeps getting bigger and keeps adding more to it, you get larger values that take place. Or cells that get going in cancer cells, they kind of work in this exponential range as well, because they keep expanding and keep growing at rapid rates compared to other things. And so you get these exponential curves in there and what takes place with them. The larger the base, so the larger the base, the steeper the graph. Okay, so my graph is going to get steeper when I have that. The other thing that happens with these, so if I go back to y equals, and let's see what takes place if I say f of x is equal to a negative 2 raised to the x power. So let's see what goes with that one. So if I put parentheses negative 2, I need to put it in parentheses because when I raise it to a power of x, it's got to have and show me what pieces are going and taking place in there. So if I hit graph, that's my first one. Did my other one change? I don't even have it in here. I don't think I have it in here. Let's go back to y equals. Let's turn that one off. It's thinking. I think I gave it something it's not capable of doing. So you want to make sure that with your bases that you have, that your bases are positive, because again, they're not going to work if we don't have them being positive. So I'm going to delete that piece. If I said divided by, second insert, divided by 1 divided by 2, oh, but I don't want a negative 1, I want a positive 1, so I'm going to delete that piece. So if I put a half in front of there, let's see what my graph comes out now as. And the half reversed it. Notice it took it and it flipped the parabola around. So if I have f of x is equal to 1/2 raised to the x power, my graph shifts and it's decreasing. So I get a decreasing graph here. This one's increasing. This one's decreasing. Yep. I better write that. So it's decreasing. So it's kind of going the opposite direction. So with a fraction, I get a decreasing graph. With a solid whole number valued base, I get an increasing graph. And that part starts changing with what takes place. The functions that they give you in Hawks, you will simply put them on and put them in your graph category and let the calculator figure out what the graph looks like and do some comparisons between your different graphs. If I were to take this and say I have 2 to the x power plus 4, this 4, just like the k did in my parabolas, remember parabolas and our k moved it up and down the y-axis, that's the same thing that's going to happen here. That 4 is going to move it from one spot to another, and so that's going to end up creating and making a change in what I happen to have for those. Is the domain changed at all? No. Domain still remains as all real numbers. Does the range change? Well, the range is always going to be limited by what you can have in here. If it's coming and getting closer to x, your range has to be greater than 0. Okay, not equal to 0, but greater than 0 to end up figuring out those. I don't think it asks you in there about ranges and domains. So then the other part, now let's see, we'll throw in a couple more problems you got to take a look at. One they might give you is r of x is equal to 0.5 times 8 raised to the 0.8x. Now when they give you something like that, you're going to enter it into your y equals. But be really careful when you're entering that. So if I go back to y equals, clear out what I have, and I put this in, I'm going to put 0.5 times 8 caret 8.0 or 0.80, sorry, x. And when I do that and I get my graph out of it, you want to see what happened. What happened? I didn't get what I was supposed to get, did I? And the reason I didn't get that, and I wanted to show you this, is because in my y equals, I have 0.5 times 8 caret to the 0.8. Now what my graph did is it just said I had 0.5 times 8 to the 0.8, but x was not associated with the 0.8. Okay? So really what I need to do when I put this thing in here is I need to put that whatever my exponent happens to be, I need to put it inside of parentheses because then it will raise the whole thing, this whole value, to that amount. So make sure that you put your parentheses around whatever your exponent happens to be. And now if I hit graph, I get what I wanted to get. And it's an exponential graph because it's going across here and it's going up. So if you ever end up with a straight line when you're putting your stuff in, it's probably because when you entered it in, your graph, we want 0.5 times 8 caret, but put whatever your exponent happens to be inside of parentheses. So make sure you put it inside of parentheses to come up with that value. So you want to make sure that you get that graph and get your stuff in there the way that should be. Okay? Does that make sense? Now, some of them also have things raised to, let me see if I can find one here. Oh, here's one. F of x is equal to a negative 3 times 5x plus 3. Now, if you got a plus added to that, make sure you put that whole exponential part inside of parentheses on your calculator to calculate out what your graph will be. So if I put this one in there, clear out what I have, negative 3 times 5 caret parenthesis x plus 3 parenthesis. Don't forget to close it in a parenthesis also. And I get my graph. Whoops. What did I type in there? Oh, didn't hit a negative, hit a subtract instead. Okay. And what did it do? Flipped it upside down, same thing as it does to parabolas. With that negative 3 out in front, just like my a in my parabola, it told it to go upside down as well. So I'd have to pay attention to my graphs. Now in Hawks, it's going to give you 4 graphs. It might give you one that looks like this. It'll give you one that looks like this. And they may give you one that looks like that. And the third one may look like that. And you need to pick out which graph makes the most sense. So when I look at all of these, I would say that I would pick this graph. So it's going to give you 4 graphs to look at in your comparisons with those. Okay? All right. Again, it's just plugging those in and going from there to see what happens with them. The last piece in 10.3, or 10.3, 11.3, is the story problems. And these aren't bad, so don't say, oh no, they're story problems. I'm going to have to get in a panic over what's taking place with these. They will give you, in most cases, and when I pick questions for your test on these story problems, I will pick ones that have your equation in them. You do not need to memorize the equation or the exponential formula that you need to use, because they will be automatically in your problems. If you take a look at most of these, here's one down here that's got it in there. The only ones that do not, and we'll talk about that when we get there, there's one that they don't put that in. Yes?
I'll have one.
You don't have one? You will have one. You didn't get one either? Who else? I think there's 3 of you there that didn't get one. Emily, did you get one of these? You didn't get one. Did you get one? There. Hate to leave you without it. It's just a matter of taking these and plugging in what you have to put into them. So in this case, a scientist has 12,000 bacteria present when T is 0. So T is 0, T meaning time, when this whole experiment starts. And she knows the bacteria grows accordingly to the function of y equals y sub 0, 3 raised to the 0.25 t when it is measured in hours. How many bacteria will be present at the end of one day? Oh, what in the world do we have here? The y's in here are bacteria. The y is the ending bacteria. The y sub 0 is the beginning bacteria. And the T represents hours. So all I got to do is replace my letters. So I want what I'm going to get for an ending bacteria from my starting bacteria. Bacteria is kind of nasty. It's got lots of growth potential in it. Times 3 raised to the 0.25. But what am I going to times that by? What's T going to be? T is going to be 24. Yeah, because there happens to be 24 hours in a day. Okay, so we're going to put 24 in there. So then if I just simply go and get out of my, and clear my calculator out here, get out of my y equals, go to just my normal screen, I'm going to put 12,000 times 3 caret. Now the same thing I have to do with these exponents as I did with graphing them. They need to go inside of parentheses. 0.25 times 24 parenthesis. And you're going to hit enter, and we will find that her 12,000 bacteria became 8748 with 3 zeros after it. Became 8,748,000 bacteria in one day.
Can you put that in scientific notation?
I think it's going to ask you for it in regular. I don't think it asks you for it in scientific. All the numbers that come out with these are all numbers you can type in. There won't be any of them that are really huge. So what does that mean? So if she ran this for 2 days, just think what's going to happen. Okay? For 4 days, what's going to happen? I think bacteria could take over everything if it so chose, because it grows so rapidly and so fast. But that's what exponential stuff does. Then if you go down to this next one, same basic situation. It says determine the exponential function that fits the following information. Y to the 0 is 7,500 bacteria, and there are 12,000 bacteria present after 4 days. Use this to figure out what T is in days, and what we'd end up coming up with for this. So what happens with this one is your Y is your 12,000. Your Y0 is your 7,500. Your B, do we know anything about B? We don't know a thing about B, because that's what we're trying to find out, is what that value would be. But I know T is 4 days, correct?
Yeah.
Okay. So, what was that again?
You times it by 24 for
Yeah?
hours, or is it just days?
You think so?
I don't know.
You're guessing?
Yeah, I don't know.
Let's see if you're right. Okay. So what I have to do with this thing is solve it. So I would have to take and divide by 7,500. So I'm going to take 12,000, divide it by 7,500. And that leaves me with 1.6 is equal to b to the 4th power. How can I get rid of that 4th power? What was that? The 4th root. Perfect. Yeah. Take the 4th root of this side and the 4th root of that side. It's going to leave me with b. So how do I get to a 4th root? Well, under math, we have different roots in there. So if I go to math, first I got to put my root in. Sorry. Put 4 in on your calculator. Go to math. Go down to number 5, because that's my xth root. And then put in 1 or 0.16 or 1.6, I should say. Close it and then put parentheses in there. Hit enter, and it's approximately 1.124. And sometimes it'll tell you where to round off to. Would be what I'd end up with. 1.124 or 5, because the 6 is going to make it become a 5. So that would become my answer. Okay, for this one. Let me put the 6 after this. So it's just kind of putting stuff together. The interest ones involve an interest formula, and they tend to get into doing all the interest, because interest is an exponential growth if you're figuring stuff in the correct manner. So P is the principal. R is the rate in decimal. H is the how it is applied. Whether it's annual, which would be H would equal 1 if it's annual. If it's biannual, H would equal 2. If it's monthly, H would equal 12. And if it's yearly, they tell you later on that a yearly for a bank is 360. I don't know what happens to your 5 days. I guess they get freebies there for your 5 days. But that's what H would end up representing. And then T is the number of years. So T would equal years. And so if we look at this very first one in here, yeah, get some paper here. If P dollars are invested at a rate of interest R in decimal form, compounded annually for T years, the amount A becomes this formula. So we're going to use this formula and not that one. But this one shows up later on, so I guess that's why I put it in that spot. Find the value of $13,000 invested at 5% for 4 years. So $13,000 is my principal. My rate is 0.05, and my T in this case is 4, and you can of course put that on your calculator, and what do we end up with? So if I put my calculator in here, I got 13,000 times parenthesis 1 plus 0.05, and be careful, make sure you put 0.05 and not 5, parenthesis caret 4, and hit enter. And so after 4 years, you would be taking out of your bank, if you could get 4% interest, $15,801.58. Okay. Of course, interest today is terrible.
We got our house interest at 1%.
Mortgage interests are wonderful because you get low ones right now, but in the bank, if you got any money, my amount I earned this year was $10 for a whole year of interest. Yeah, major, $10. Boy.
Yeah, man.
I'm used to, you're used to putting in like $300, $400 in interest or in stuff, but not today. Okay, so if we look at the next one, what will be the value of the principal investment of $1,300 invested at 5% for 4 years if interest is compounded monthly? Now that's where your H comes in here, because it's compounded monthly. So basically it's the same kind of thing. You're putting in less money. 1 plus 0.05 divided by 12, because H is representing the number of months, and 12 times 4 years on the outside. So what comes out of that one? So if we stick that one in our calculator, 1,300 times parenthesis 1 plus 0.05 divided by 12 parenthesis caret parenthesis 12 times 4 parenthesis. Again, don't forget to put your exponent parts in parentheses. So now I have $1,587 and 16 cents. By compounding it that way, you end up getting a little bit more. And then finally, the last one with interest is find the value of A. If $1,300 is invested at 5% for 4 years, and interest is compounded daily, and we're going to use 360 for H. So if you already have it on your calculator, I like to sometimes just pull back up what I had, because all I really need to change from that problem to this problem is, instead of having 12 in there, I need to put 360. So I use my insert button and put 360 where 12 was at. Or you can retype the whole thing. Delete my 12. Second, insert 360, hit enter, and I made a whopping 74 cents more. Big improvement. Not much of an improvement. But I think you get the idea of just plugging these things in, and that's basically the only piece that you have. One other part that we need to talk about is when you get into the next formula, there's an E in here. And an E is a representation of that compounded interest piece that we just got done talking about. And on your calculator, you have an E to the x power. It's above your natural log, or your ln key. Let me move it up here. Your ln key has an E key above it. And you just use that key in place of the E within your problem. And if you hit that second E to the first power, it will show you that what E is equal to is 2.7182818828. Beautiful number there. When I was doing these before we had calculators, which doesn't seem that long ago, you had to remember that. It was written out for you, and you had to put it in your brain, and every time you ran across an E, you had to stick this number in and hope for the best. Okay, so you guys at least got it easy. You can just hit a button and boom, it's there. You know, so if we were going to do this problem that's in front of us, and we use this E key when we get into natural logs with the ln key, and the E to the 10th power comes up quite a bit later on in this chapter. So that's why we have to introduce it at this point. So if I put 46, because it says find the amount of money that will be accumulated in a savings account if $4,600 is invested at 6% for 6 years. So in here I have my P, I have my E, my rate is 0.06, my time, which is the T that's in there, it's supposed to be a T, it looks like an I, is 6. And so what's my interest if I do that one out on my calculator? So on my good old handy dandy calculator, I'm going to take 4600 times second, bring up my E. It puts a parenthesis in there, so 0.06 times 6. Close it in the parenthesis, hit enter, and if I have it compounded continually, I get $6,593.32 kicked out in the tail end. Okay, I think in Hawks, this is the one. If you see compounded continually, you're going to use that formula. That's the only one in there that they don't put it in for some reason. Don't ask me why. All the rest of them they put formulas in for you to use. But do you think we got the idea of what you're doing with these? So this one here, same situation. Sees your original price, and this one's a depreciation, so it's going to be 527 is my cost times 1 minus my rate raised to my time, and it's at 2 years. So again, plug it in and you'll see what you get out of that one. And the last one, same thing in here too. Plug in your pieces and see what comes out of them. I guess there's 2 more. There's this one, and the last one was this one, but I think we got the idea. It's another one of those compounded continuously problems. So when you use your E, the E key, is that what you're talking about?
Yeah.
Okay, it's your second button and above your natural log if you've got a TI 83 or 84. So it's that E to the X key that's above that. Okay?
Oh, okay.
You find it?
Yeah.
Okay, good. Good question to ask, because again, you have to have that in place if you're going to get anything out of that.
I'm taking my test today.
All right.